the damped harmonic oscillator model for, well, it's easiest to imagine in terms of a mass on a spring, but if you're in electronics, you know that this model can apply to electric circuits as well. The parameters in the case of a mass on a spring are the mass, m, that gets multiplied by the acceleration, the damping coefficient that gets multiplied by the velocity, and the spring constant that gets multiplied by the position. That's a second order linear differential equation modeling a mass on a spring. Again, mass m, standard units would be kilograms. Damping or friction constant b, I guess units for that would be like newtons per meter per second. You got to multiply it by meters per second to give you units of newtons. Ultimately, this equation comes from Newton's second law, F equals ma, after rearranging. And K, the spring constant coming from Hooke's law, measuring the stiffness of the spring. Larger K means stiffer spring. Units would be like newtons per meter, I believe. Yeah, Y is in meters. The product is in newtons. Equaling 0, there's no external forcing here. That's your damped harmonic oscillator model. M, B, and K are all positive constants. Let's take a particular example, and for sake of quicker writing, write it in prime notation. Let's pretend M is 1 for the sake of simplicity. And let's make B be, let's say, 10, and K be 21. I'm purposely picking these numbers to work out nicely in the end. If all you're after is a solution to this second order equation, and by the way, it's a homogeneous equation because the right-hand side is 0. Some more ideas here. In finding the solution set of this equation, you're really finding the kernel of a linear transformation. Not a matrix, there's no matrices there, right? But a more general kind of linear transformation. I'll talk about that more as we go. But as far as finding a solution to this, what we typically end up doing is we end up guessing. That's a U there. Guess y equals e to some constant times t, hoping that such a guess will work. Now, will it work? Well, I've made it to work in this case, but it's not obvious that this kind of guess will always work, because like what if there's cosines and sines involved? What if the mass is oscillating back and forth? Turns out this particular equation has enough damping that there's no oscillation. It's an exponential decay. It's like the mass is inside it's inside glue or something, okay? And there's no oscillation. The amplitude decays to 0 very quickly. But in some cases, you would imagine there could be oscillation. So wouldn't you guess cosines and sines? Or maybe an exponential decay times a cosine like we saw last week? Yeah, things can get more complicated, and this guess could be problematic, so to speak. Though we'll see eventually in chapter 4 that it can be fixed when S is a complex number. You can actually, when S is a complex number, this guess can still be good and involve ultimately oscillations in the mass. Well, let's see what happens if we go ahead and guess this. Find y prime, find y double prime. S is a constant here, so I use the chain rule a couple times. Substitute in to the differential equation. Y double prime is s squared e to the st, plus 10y prime will be 10s e to the st, plus 21y will be 21 e to the st. I want to set this equal to 0, and I'm asking, are there any values of s that make this equal to 0, no matter what t is? This is really important, what I just said there. I'm asking, are there any values of s, any constant values of s is a constant, that make this always equal to 0, no matter what t is, for all t? little bit of factoring reveals that the e to the st doesn't really matter. E to the st is never 0. Although I joke with you engineers that sometimes engineers say e to the minus infinity is 0, but right, wait a minute, infinity is not a number. If you had to say e to a power was ever 0, you would say e to the negative infinity is 0. But we're dealing with numbers, not infinity here. So this is never 0. So the only way this is 0 for all t is if s squared plus 10s plus 21 equals 0. And I did that, make that nice to factor as s plus 3 times s plus 7. I purposely did that. Of course, in general, you'd have to use the quadratic formula, and you could get irrational number roots and things like that. And it's kind of an unpleasant thing in that case. Or you could get complex number roots. Yeah, we'll deal with that later in the semester. Two possibilities for s, -3 and -7. And you could double check if you plug those in for s, you would get something that works. What this ends up meaning is the two functions, therefore, e to the -3t and e to the -7t are solutions. More than that, these solutions are not scalar multiples of each other. There's no constant you can multiply either one by to get the other one. And what that ends up meaning, as we're going to see in lectures 17 through 24, is that these are called linearly independent solutions, and there's two of them. And yes, the kernel of this linear transformation is going to be a two-dimensional vector space. Lecture 15b introduces the idea of a vector space. Lecture 16b goes into more detail. What is a vector space? You understand what vectors are, right? Arrows in the plane or in 3 space, or maybe even an n-dimensional space that can be added, multiplied by scalars. And all the algebraic properties that you would hope would be true are true. They're very nice. The commutative property, v plus w equals w plus v. The associative property, it doesn't matter where you put parentheses. There's a 0 vector, that's the additive identity. V plus 0 is always v, no matter what v is. There are additive inverses, all that kind of stuff, whose descriptions and symbolic representations you should work on remembering, even though you can use a note card for the in-class exam. Should work on trying to remember those things and the names, associative, commutative, those kinds of properties. It'll be beneficial for you to try to work on remembering those things. All those things work not only for ordinary vectors, but also vectors that are functions. Huh? Yeah, I'm calling these two functions vectors. That doesn't mean I should draw them as arrows, though. It means I should think of them algebraically as things that you can add and multiply by scalars and that kind of thing. And all the usual algebraic properties still work. That's what it means. Don't try to imagine them as arrows. That's not what I mean when I call these vectors. The solution space. So therefore, these are solutions. In fact, what are called linearly independent solutions. And more than that, they're going to span the solution space. What does that mean? It means any solution of this differential equation is a linear combination of these two functions. What I'm saying is very important, more so for exam 3 than exam 2, but still relevant to think about for exam 2. Any solution of this differential equation, which is really the kernel of a linear transformation, this left-hand side of the differential equation really defines a transformation. How? Give me a function as input, compute its second derivative plus 10 times its first derivative plus 21 times the function to get the output. Say that again. This left-hand side really defines a linear transformation. that takes any function, well, that at least has a second derivative as input, computes the second derivative, adds 10 times the first derivative, and adds 21 times the function to get an output. Now, if you do that with most functions, like a cosine or a logarithm or something like that, although with logs, you'd have to say t can only be positive, you're not going to get zero. You're not going to get the zero function. In fact, with most exponential functions, you're not going to get the zero function. But with these two, you will get the zero function out. They're in the kernel of this linear transformation. A more abstract kind of linear transformation. No ordinary column vectors, no matrices. It's a more abstract idea. Turns out these two linearly independent solutions will also span the solution space, which means the solution space is two-dimensional. And the solution space consists of all linear combinations of them. Like this, as C1 and C2 vary over the real number system. The solution space is a two-dimensional vector space. But there's no arrows going on here. It's a purely algebraic symbolic thing. Could I possibly imagine these things as arrows? I wouldn't recommend it typically. Maybe points in some abstract space. The functions, each function is a point in an abstract space. It's an object, it's an element of some abstract space. That might be worthwhile. Actually, we will see that is worthwhile to think about. But I'm going to avoid thinking of them as arrows. That is the solution space. What I'm talking about here is lecture 15b and 16b stuff related to differential equations, though. The linear algebra and the differential equations are going to start to become very, very tied together right now here in lectures 15 and 16, and then after the exam in lectures 17 through 24. Very, very much tied together. This is still relevant a little bit for exam 2 here. This thing is a general solution of the differential equation. Notice it's a scalar function, right? No vectors in the ordinary sense of vector. It's for any given value of t, that's a number. The output is a number. The entire object itself is a function, or in fact, a family of functions, two-parameter family of functions. There are infinitely many solutions of the differential equation because C1 and C2 can be anything. If you have an initial value problem, an initial position of the mass, and initial velocity, typically you let the mass go from rest, but hey, what's from stopping us from hitting it with a hammer and giving it some initial velocity? Now you might quibble with that and say, well, even if I hit it from a hammer, isn't it still starting to move from rest? And the answer is yes, that's probably right. But for the sake of simplicity in modeling, assume the hammer hit is instantaneous, so that the velocity is something, the initial velocity is something non-zero. That just makes it simpler for modeling's sake. Can we relate this to ordinary vectors? Yes, and this is something else I want to emphasize. Go back to our differential equation. Y double prime plus 10y prime plus 21y equals 0. That's a homogeneous equation because the right-hand side is 0. We will, in chapter 4, look at non-homogeneous equations where the right-hand side is maybe a cosine or something. It's forced. It's like you got a mass on a spring moving back and forth on a table, and you're shifting the table back and forth like that. That's like adding an external force. Not now. You should be able to convert this to a first-order system. That's a big point of emphasis in the textbook, right? Convert it to a first-order system of equations so that you can draw the vector field and think about solutions in the vector field. So one basic thing you should be able to do is convert this to a first-order system. How? You start by defining the velocity to be the derivative of the position. In this equation, yes, y prime is the velocity, but you don't see any v's. To convert to a first-order system, we are introducing the letter v, a new variable. And the first equation in the first order system is essentially a definition. V is defined to be dy dt. That's just a definition, nothing fancier than that. I'm defining the velocity to be the rate of change of the position. The second equation, which is a first order differential equation for dv dt, has to come from the scalar equation by solving for y double prime, which is v prime, based on defining v in this way, by subtracting 10y prime and 21y from both sides. But once again, y prime is v. This is negative 10v minus 21y. Careful though, a common mistake here people make. I mean, it's technically not a mistake to write 10 minus 10v minus 21y here. That's technically not wrong, but it's ideal for the purpose of writing a matrix to put the y term first and the v term second. So down here, I'm going to write it as minus 21y minus 10v. Again, it's not wrong for the system of scalar equations to write minus 10v minus 21y in the same order I have here. But it's more convenient to put the y term first, v term second, so that now if I write this in vector matrix form, I get the right matrix. That's really important to get the right matrix. Now I'm going to let the vector y, capital Y, have components little y, little v. Yes, that's a little weird, but okay. Write this as this system of two first order scalar equations as a single first order vector equation. What is dy dt? Well, it's a vector whose components are d scalar y dt, dv dt. And what does that equal? It's by the differential equations. It's the first component's got to be v, and the second component's got to be negative 21y minus 10v. That is a vector field. I could think of this as a vector f of vector y if I wanted to, for the purposes of emphasizing in my mind that it is a vector field. Though if I do that, it's convenient also to imagine y as a row vector, so to speak, like this, or a point, because when you draw vector fields, remember, you imagine taking any point in the plane and plugging that point into the vector field to get an output as an arrow that would be drawn at the given point. So you can write it either way. It's okay. I know there's lots of inconsistent notation in this class. We're real flexible with our notation. Different notations have different points of emphasis. That's why the different notations are used. Don't let the different notation bother you. But it is also a linear system. We got first order, well, v and y to first powers in this thing. No constant terms. It really can be thought of as a linear transformation, a matrix times the vector y. And here's where the order matters, because to get the matrix right, you want to have the y term first and the v term second. The matrix is ultimately 0, 1 for the first row, negative 21, negative 10 for the second row, not the other way around. If you're multiplying it by a vector whose first component is little y and whose second component is little v. And this can be thought of as capital A times the vector y. So real important, but fairly basic thing here is being able to take the second order equation, write it as a system. Sometimes on an exam, especially an in-class exam, I just say, write down the corresponding system. There it is. That's all you have to do. Maybe write it in vector form. You do it like this with a matrix A. Write it as a matrix times a vector. Why are these equations true? Again, this is just a definition, effectively. That equation is just what it means to differentiate a vector whose components are functions of t. You don't see any of t's in here, but that's all assumed. That's just, well, it comes from the system of differential equations. This is what it means to multiply a matrix times a vector. There's a linear combination idea of the columns in the background there, though I skipped the step. And this is just renaming the matrix A, and the vector Y is right there. What have you done so far with this? You have tried to draw vector fields. You could do a little bit by hand with simple examples, but once you get to even an example like this, you pretty much don't want to do them by hand anymore. I will try to show you something, a rough sketch of the phase plane by hand here. Then we'll compare with Mathematica and see how it looks. For the phase plane, you don't have to think about the matrix. You could go back to the system and think about what I called null lines in the lectures. Null lines don't come into the textbook until much later, chapter 5, but I like introducing them early, chapter 2, because I think they're super helpful. This is all part of our review. This is all stuff that's been stuff you've been learning about recently. Just trying to put it all together in your minds here. Let's rewrite the system once again. My focus is going to be on drawing the phase plane, or phase portrait is probably a better way to say it. Here's the system in scalar form. To help me start drawing the phase plane, which is a generalization of a phase line. Phase plane is a two-dimensional generalization of a phase line from chapter 1. That's why the book introduces phase lines in chapter 1, is so that we can do phase planes in chapter 2. And maybe phase spaces later on. Three-dimensional space or n-dimensional space. In this case, since y is the first variable and v is the second variable, it makes sense to label the axes y and v. But we had an example last week where we labeled them x and y because the dependent variables in your system were x and y instead of y and v. Just like with phase lines, you are interested in equilibrium solutions, equilibrium points. How do you find those? You set the right-hand sides equal to 0 and solve for v and y in this case, if you can. Well, this system of linear equations, ignore the derivatives, that's a linear system of algebra equations. It's also homogeneous, and the matrix has a non-zero determinant. Reviewing determinants here. That means this is only going to have the trivial solution. The kernel of linear transformation would be trivial. That means there's only one equilibrium point here at the origin. 0, 0. With null lines, though, we can just think about each equation individually. V equals 0 does define a line in this YV plane. What line? Where is V equal to 0? On the horizontal axis. That's where V is 0. This horizontal axis, the y-axis, y is horizontal here, is where V is 0, because V is the second coordinate. That line, if you think about it with respect to the differential equation, is a line where the vector field would be vertical. Arrows in the vector field would point straight up or straight down because dy dt is 0 along that line. And y is the first component. Solutions have to have vertical tangents there because dy dt has got to be 0 there. So you're going to make a bunch of little vertical lines when you're doing this by hand on that line there to emphasize the vector field is vertical. Solutions cross that with vertical tangents, either straight up or straight down. The other equation is, in this case, the v null line. This is the y null line. where dy dt is 0. Y is horizontal. The v-nocline, v is vertical, is where negative 21 y minus 10v is 0. That's the v-nocline. Solutions will cross that with horizontal tangents. Vectors in the vector field will point straight to the right or point straight to the left. But how do you draw that line? Since v is vertical here, it's probably best to solve for v as a function of y. Add 21y to both sides, divide both sides by negative 10. There we go. This line in this plane is going to have a slope of negative 2.1 and go through the origin. It's going to look about like this. And with regard to the vector field, the vectors have to be horizontal. Solutions have to cross that with horizontal tangents. These are the noclines. That one's the v-nocline. Happens to be the y-axis in this case, but in general, it doesn't have to be. This one's the y-nocline. No, excuse me, I got them around mixed up. This one's the y-nocline. This one's the v-nocline. The y-nocline is where dy dt is 0. The v-nocline in this context is where dv dt is 0. How do you start drawing the vector field in solutions? You can also just maybe draw a couple vectors in the vector field, like maybe one right there, where y is positive and v is 0. If y is positive and v is 0, well, dy dt is 0, and dv dt would be negative. I'd have to have an arrow pointing downward. Should I make it really long? Technically, from the vector field, you should, because those are big numbers there, negative 21 and negative 10. And if y, for example, is 1, I'm going to have a vector 21 units long. But that's very unpleasant to draw lots of vectors for. So we shorten them, and we really draw what's called the direction field instead of the vector field. Make the arrows all have the same length effectively. Scale them down. Because all we're after is the direction of solution curves when we draw the phase plane. Yeah, in the back of our mind, solutions are really moving fairly fast because the actual vectors in the vector field are longer. But all we're after is directions here for the most part. And if you draw some more vectors, you'd get some rotation going on here. Does that mean solution curves are periodic functions? No, it does not. What does it mean? It's tricky. Yeah, it's tricky here. And I'm wondering if I fully drew this right or not. I should probably be more careful. I was assuming this one goes this way, but I'm actually not sure. Let's pick one point on here. Let's pick the point yv equals, by this equation, I could pick y is 1 and v is negative 2.1. I should really ask, is dy dt positive or negative there? And actually, it's positive. I was wrong. I was too cavalier. It's actually going to point this way. Oh boy, I'm feeling confused though. Does that make sense? I feel like something's wrong here. Were they read the first time dy dt? Oh, because v is negative. Sorry. Okay. Okay. It seems like there's oscillation going on here, but I know there can't be. Because I know the scalar function doesn't oscillate, the scalar solution. And that would mean the vector solutions don't oscillate either. So what's going on here? It's not obvious, but I think the solutions go like this, and I think they head to 0 pretty quickly after that. I think that's what happens. This is where there's limits on how much you can do by hand, and we need to rely on technology. There are some other things we can do by hand here that I haven't done that we'll see in chapter 3, related to something called eigenvalues and eigenvectors, which maybe you've heard of before. But I'm not doing those now because that's chapter 3. So at the moment, I'd be more relying on well, my experience with this kind of stuff and trust that the solutions decay to zero without oscillating. All right, let's use the technology now. If I was going to plot this with Mathematica, yeah, vector plot makes vector fields as well as slope fields. Difference with compared to slope fields is you don't put a 1 first. You put the right-hand sides of the system, v first and negative 21 minus 10v second. Negative 21y minus 10v. But in the labeling the axes, y is horizontal, v is vertical. I want the y first and the v second. Okay, let's just see what it looks like. Nice to get rid of the frame maybe and add in axes as well. Let me also put the stream plot in there. You can add the stream plot with show. Show just combines different graphic objects together. I think I want to put maybe the stream plot second here. Syntax is very similar. Just change the word vector to stream. And to make it brighter, we could do stream style blue. Let me also get rid of the frame, arrow false, axes, arrow true, we'll add axes. Okay, that's feeling better. It's not a very bright blue. I thought it usually makes it brighter. Let's make it cyan, make it brighter. Why is it okay? Why am I not seeing the stream plot very well there? Okay, Mathematica has changed how they do things. I mean, it's drawing the streams different colors. You see sort of yellow and orange over here and purplish in here. But I am seeing, let's not worry about those details. I am seeing solution curves, which is what the stream plots show, heading towards zero effectively. And they are crossing that null line that's going to look about like this, where they are horizontal. It's a little hard to see, but there's some horizontal tangents to solutions right in here. This stream in the stream plot looks like a straight line. That's called the straight line solution. We're going to talk about those in chapter 3. It's not the null line. The null line's a little bit more over here. It's hard to see, but we are seeing the solutions head towards zero pretty rapidly in the end. Something new introduced at the end of lecture 16A is something called the matrix exponential. Let me enter the matrix A here. It's the last thing we do of this topic. Then we're going to do our quick, more general review. This is still, again, though, stuff you want to know for the test. There's my matrix that I had. A very, very important thing for us related to differential equations that's not in our differential equations textbook is going to be the following. If I write down an arbitrary linear differential equation in matrix vector form, and also an arbitrary initial condition, y of 0 equals y naught, as vectors, the unique solution of that, it turns out, can be written y equals, I'm going to use my phi notation, equals phi, capital Phi in this case because it's a vector, sub y0 of t, and that's going to be the same answer you would get as if you pretended everything was a scalar. If you pretended all these quantities, the y, the a, were all scalars, what did we see even back like the first week of class? We saw this was like the constant, the initial condition times e to the at. It's the same thing here in the matrix vector situation, except I'm going to put the e to the at first. E to the at times y naught, the initial condition. It works still in the matrix vector situation, except you need to realize that, well, first of all, the y's are vectors. And this e to the at is now a matrix. It's called the matrix exponential. This is introduced in 16a. That is the solution. Well, that just begs a question. Well, how do you find the matrix exponential? Do you just take the entries of A and make them powers of E and multiply by T? No, you don't, except in very special cases. Last week, you might remember, I said a big purpose of the linear algebra content was to compute A to the n power, where A is a matrix. We were doing a difference equation, and we needed to compute A to the n power. You did that last week. It was the rotation matrix. Cosines and sines were involved. With the differential equation, the big thing is computing this matrix exponential. And all the theory we're going to do very soon, over the next 3 or 4 weeks, is going to be related to computing those things. Not all the theory, but a lot of the theory. It's also related to change of coordinates, way back in the first week of class. For the moment, we can just have Mathematica compute the matrix exponential. Mathematica, in matrix form, what is the matrix exponential of A times T? It's that. That's a matrix. It's a 2 by 2 matrix. Upper left entry this, upper right entry this, lower left entry this, lower right entry this. It's a function of T. It's a matrix valued function. Give me any real number T, I get a matrix out. Blow your mind. And if you multiply this matrix times an arbitrary initial condition vector, you get your solution of the initial value problem. How is this computed? We have to wait. Now we're just trusting the technology. But if you do multiply this times an arbitrary initial condition vector, I do want you to know that the result is a vector now that you could plot in the phase plane. It would be a solution curve. It would be a parametric curve in the phase plane. Always keep in mind with these phase planes that solutions are parametric curves that follow the vector field. They're functions of T. You don't see any T's here. You got to imagine it in your mind. The textbook does that by emphasizing going back and forth between the phase plane and your solutions as functions of T, right? You've done problems like that last week. That's not an easy thing to do, but it's something worthwhile to work on. In this case, what would it be? Y is a function of T and V is a function of T. 2 separate graphs. Well, it depends on what your initial condition is. If your initial condition is right there, Y starts at 1 and decays to 0. V starts at 0, goes negative before decaying back to 0. That's a quick 2 sketch of Y and V as functions of T based on this graph right here. This parametric curve helps me see how Y and V depend on T. I don't know the scale on the T axis here. The Y axis would, if this is a 1 here, that should start at 1 there. And V is starting out at 0 because I'm starting on the Y axis, so it starts there. Y decays towards 0 because you're moving to the left. V goes negative because you're moving down to the negative region here where V is negative before going back up again towards 0.